It is still lying exactly where they left it. 42 meters of solid pink granite, cracked clean through, abandoned in the bedrock of a quarry in southern Egypt for nearly 3,500 years. If it had been finished, it would have stood taller than any obelisk Egypt ever raised, weighing close to 1,200 tons, heavier than 2.5 fully loaded Boeing 747s, carved from stone harder than the steel of a modern hammer. The workers who started carving it never got the chance to stand it upright in some temple courtyard. They never got to watch the sun catch its polished sides at dawn. Partway through the work, a crack split through the granite, and whoever was in charge of this project made the only decision that made sense. They stopped, they left it, they walked away. And in walking away, they handed the modern world something far more valuable than a finished monument. They left behind a crime scene, a perfectly preserved, frozen-in-time record of exactly how a civilization, without iron tools, without explosives, without any machine more sophisticated than a lever and a sledge, took on one of the hardest stones on Earth, and won again and again on every other obelisk that did get finished. This is the unfinished obelisk of Aswan, and the tool marks carved into the trenches around it have been generating genuine scientific argument for 200 years, not because nobody has an explanation, because the explanation that exists, the one supported by thousands of physical tools still lying in the dirt where workers dropped them 3,500 years ago, it keeps turning out to be more complicated, more impressive, and more contested than anyone initially assumed. To understand why this rock has confused experts for 2 centuries, you need to understand exactly what they were dealing with. Granite is an igneous rock, formed from slowly cooling magma deep underground, and it sits at roughly 6 to 7 on the Mohs hardness scale, the standard measurement geologists use to compare how easily one material scratches another, running from 1 for the softest minerals up to 10 for diamond. 6 to 7 is hard. Quartz, one of granite's primary mineral components, sits at 7. This is stone that laughs at a fingernail, laughs at a steel knife blade, and only barely yields to the kind of carbide-tipped tools you'd find in a modern stone-cutting workshop. Now consider what tools the Egyptians of the Old and Middle Kingdoms actually had access to. Bronze was the most advanced metal available to most of Egyptian history. And bronze sits at roughly 3.5 on the Mohs scale. Copper, used even earlier and still in use through much of pharaonic history, sits at around 3. Both metals are dramatically softer than the granite they were supposedly cutting. Basic materials science says this should not work. You cannot cut a harder material with a much softer one, at least not through simple slicing the way a knife cuts butter. And yet, granite obelisks, granite sarcophagi, granite temple casings, and granite statuary survive across Egypt in numbers that prove, beyond any reasonable doubt, that the ancient Egyptians were working this stone constantly, skillfully, and at a massive industrial scale for thousands of years. The answer to this apparent contradiction lies at the unfinished obelisk itself. In a detail that is almost shockingly mundane once you understand it, the Egyptians were not slicing granite with metal blades. They were pounding it into submission with stone. When archaeologists first mapped and documented the unfinished obelisk site systematically in the 1920s and 1930s, they found something scattered across the quarry floor in genuinely staggering quantities. Round, fist-sized to head-sized balls of an extremely hard, dense, dark volcanic rock called dolerite. Thousands of them. Tool after tool after tool, abandoned where workers had dropped them when the project ended, or worn down to uselessness and discarded after countless impacts against granite that simply would not yield to the wood and copper tools available for finer work. Dolerite sits at roughly 5 to 6 on the Mohs hardness scale, harder than the bronze and copper tools the Egyptians otherwise relied on, and close enough in hardness to granite that it could chip and crush the surface through sheer repeated percussion, even without being able to cleanly slice through it. The technique was not cutting in the way we typically imagine cutting. It was controlled pulverization. Workers, almost certainly organized into teams along the length of the trenches surrounding the obelisk, raised dolerite pounders and brought them down against the granite surface over and over and over, thousands upon thousands of strikes, slowly crushing the surface layer of stone into powder and grit, working their way down millimeter by millimeter, until a trench deep enough to isolate the obelisk on all sides had been carved into the bedrock. This is, by any standard, an almost incomprehensible amount of labor. The unfinished obelisk required trenches running the entire length of a 42-meter monument, on every side, deep enough to eventually allow the stone to be separated from the surrounding bedrock and removed as a single piece. Archaeologists studying the tool marks have identified patterns in how the work was distributed. Consistent, repeated marks, suggesting organized teams working in coordinated sections under the direction of experienced supervisors, rather than a chaotic mob of laborers swinging stones at random. This was industrial-scale stone removal, organized with the kind of project management discipline you would expect from a state capable of building pyramids. But here is where the genuine scientific controversy begins, and where the tool marks themselves have generated debate that has lasted into the present decade. Because when modern researchers have actually tried to replicate this process, not theorize about it, not estimate it from a comfortable office, but physically pick up a dolerite pounder and strike granite with it the way ancient Egyptians would have, the numbers that come back raise serious questions about whether dolerite pounding alone is sufficient to explain everything we see in the Aswan quarries. In 2022, a team of researchers conducted exactly this kind of experiment directly at the site near the unfinished obelisk using close-range photogrammetry, a precise 3D measurement technique using overlapping photographs, to accurately calculate how much granite volume could actually be removed through dolerite pounding in controlled, measurable conditions. Their results, published in a peer-reviewed archaeological journal, found a quarrying speed of approximately 216 cubic centimeters of granite removed per hour, achieved at a rate of 85 hammer strikes per minute. The researchers were explicit in their conclusions. These results, they wrote, argue against the use of only dolerite pounders in the quarrying process, and support the likelihood that additional methods were also involved. Earlier experimental work, including studies referenced by NOVA's televised reconstruction attempts, produced even more modest figures, estimates suggesting a single worker might remove only 5 to 10 cubic centimeters of granite per hour through pounding alone. At rates like that, I'm scaling up to the volume of stone actually removed from sites like the unfinished obelisk trenches requires labor totals in the scale of many thousands of cumulative work hours, even accounting for large coordinated teams. This is where the second technique enters the picture, and where the physical evidence in the quarry floor itself supports a more complete and more genuinely fascinating story than dolerite pounding alone could tell. Archaeological surveys across the Aswan quarry region, not just at the unfinished obelisk, but at multiple granite extraction sites in the surrounding area, have consistently turned up charcoal deposits, ash layers, and fragments of burned mud brick in direct association with quarrying activity. This is the signature of fire setting, an ancient quarrying technique that exploits one of granite's genuine physical vulnerabilities, its poor tolerance for rapid, extreme temperature change. The technique works by exploiting thermal shock. Workers would build controlled fires directly against a granite surface, heating the rock for an extended period until the surface and the layers just beneath it had expanded significantly under the heat. Then, while the stone was still hot, they would douse it rapidly with water. The sudden, dramatic temperature differential between the heated outer layers and the cooler stone beneath caused the rock to expand and contract unevenly, generating internal stresses that the crystalline structure of granite, composed of differently expanding minerals including quartz, feldspar, and mica, simply could not absorb without fracturing. Cracks would propagate along these stress lines, weakening the stone and making it dramatically easier to break apart, pry loose, or finish removing with dolerite pounders and wooden wedges. Some researchers studying the Egyptian evidence suggest wooden wedges, driven into pre-weakened cracks and then deliberately soaked with water, were used as a complementary technique. Wood swells significantly when saturated, and the expansion force generated inside a confined crack is more than sufficient to widen a fracture that fire and percussion had already started. This is not speculation built on thin air. It is a documented, physically demonstrated quarrying method used across multiple ancient civilizations working hard stone, and the charcoal and ash deposits found, scattered through the Aswan quarrying zones, are the direct material signature of exactly this process having taken place at scale. Copper tools, meanwhile, played a real but specifically limited role. And understanding what that role actually was resolves much of the apparent contradiction between bronze's softness and granite's hardness. Copper and bronze were never used to brute force cut through solid granite the way a saw cuts through wood. Instead, experimental archaeologist Dennis Stocks, who spent decades physically recreating ancient Egyptian stoneworking techniques using only materials and tools the Egyptians themselves would have had access to, demonstrated that copper tools functioned primarily as carriers and guides for an abrasive material, quartz sand, which sits at the same Mohs hardness as the quartz crystals embedded throughout granite itself. A copper saw blade, drawn back and forth across a granite surface with wet quartz sand poured continuously into the cut, does not cut the stone through the metal's own hardness at all. The sand grains, trapped and dragged by the moving copper blade, do the actual abrasive cutting work, grinding away at the granite grain by grain. Stock's reconstructions showed this technique was genuinely capable of producing the fine, precise cuts, drilled holes, and detailed finishing work visible on completed Egyptian granite artifacts, the kind of crisp hieroglyphic carving and smooth interior surfaces that crude pounding alone could never achieve. Traces of these abrasive grains have been physically recovered from cut marks on ancient Egyptian granite artifacts, directly confirming the technique was in active use. What emerges from putting all of this evidence together, the thousands of dolerite pounders, the photogrammetric measurements of just how slow and labor-intensive pure pounding actually is, the charcoal and ash layers documenting fire setting at multiple points across the quarry complex, the copper tools that experimental archaeology has shown functioned as sand abrasive carriers rather than blades, is not a single neat technique, but a genuinely sophisticated, multi-stage industrial process. Rough removal of bulk stone through coordinated teams of pounders working in disciplined patterns, strategic weakening of the granite through controlled fire setting and thermal shock at specific points where large-scale separation was needed, wedge and water techniques to widen pre-existing fractures, and finally, fine detail work, drilling and precision finishing using copper tools paired with quartz sand abrasive, a method capable of producing results that pounding and fire could never achieve on their own. This multi-technique reality also explains something that has genuinely puzzled observers studying the quarry walls around the unfinished obelisk for generations: the presence of unusually smooth, regularly curved scoop-shaped depressions in some sections of the trench walls, standing in visible contrast to the rougher, more obviously percussive marks found elsewhere at the same site. These smoother curved sections are not evidence of some undocumented lost technology. They are most plausibly the signature of areas where fire setting and thermal shock fracturing did the bulk of the structural work, leaving behind smoother fracture surfaces along the stone's natural crystalline weak points, which were then cleaned up and regularized through lighter, more controlled finishing work. A physically and geologically coherent explanation for exactly the kind of variation in surface texture that the quarry actually shows. None of this diminishes what the ancient Egyptians accomplished. If anything, understanding the real, physically verified, experimentally tested combination of techniques makes the achievement more impressive, not less. This was not a single trick or a single magic tool. It was an integrated system of complementary technologies: percussive force, controlled thermal manipulation, mechanical wedge expansion, and abrasive precision finishing. Deployed by a civilization that had spent centuries refining each individual technique through direct, hands-on generational experience, working some of the hardest stone available anywhere on Earth. The organization required to coordinate teams of pounders across simultaneous trenches, to manage fire-setting operations without damaging adjacent work, to source, transport, and maintain a continuous supply of dolerite pounders and quartz, sand, and copper tools at the scale a project like the unfinished obelisk demanded. Reflects a level of logistical and engineering sophistication that the simplified popular image of Egyptians just hitting rocks with rocks badly undersells. The unfinished obelisk itself remains, in a real sense, the most valuable piece of evidence anywhere in Egypt for understanding this entire process, precisely because it was abandoned mid-construction. A completed, polished, fully finished obelisk standing proudly in a temple complex shows you only the final result. Every tool mark smoothed away, every trace of the actual working process erased in the pursuit of a flawless monumental surface. The unfinished obelisk shows you the process itself, frozen exactly as the workers left it nearly 3,500 years ago, the trenches still showing their pounding marks, the surrounding quarry floor still littered with thousands of discarded dolerite tools, the crack that ended the entire project still visibly running through the stone exactly where it appeared, and exactly where the ancient project managers made the calculated decision that finishing this particular obelisk was no longer worth the risk to the stone's structural integrity, the labor already invested, or the reputation of the pharaoh whose name it would have eventually carried. That decision, made by people whose names have been lost to history, preserved something far more valuable than the finished monument would have been. It preserved the evidence. 200 years of archaeological study, experimental replication, photogrammetric measurement, and material analysis have not fully closed every question this site raises. Researchers are still actively refining exactly how much of the work was pounding versus fire setting versus other unidentified techniques, still measuring and remeasuring tool mark patterns, still finding new charcoal deposits in new corners of the quarry complex. But the broad outline is no longer mysterious. It is documented, experimentally tested, and grounded in physical evidence you can walk up to and touch today at Aswan. Stone pounding hard granite into submission, fire and water exploiting the rock's own internal weaknesses, sand-driven copper tools finishing what brute force and thermal shock could only rough out. The granite did not yield because the Egyptians had some lost technology beyond our understanding. It yielded because they understood the stone, its grain, its crystalline structure, its specific vulnerabilities to heat and to repeated impact more intimately than almost any civilization in human history, and they built an entire integrated system of labor, materials, and technique around that understanding, refined across centuries of working the hardest rock available to them. The crack that stopped this particular obelisk was not a failure. It was the moment a culture that understood exactly how far they could push the stone recognized are correctly that this particular piece had reached its limit, and in walking away from it, they left behind the clearest answer archaeology has ever had to one of its oldest and most persistent questions.